This lesson is going to take us through the last part of sections 5.4 through 5.6. This particular unit is the law of cosines. When working with the law of sines, we had seen the ability to solve a couple types of problems. That would be when we have two angles and a side, angle, angle, side. What's that allow us to do very quickly? As soon as we know two angles, we automatically know the third angle. And the second thing that we handled was the good old ambiguous case. It was the one that was a little bit more detailed, where we had two sides and an angle that was not included. That's why the A is outside of the two S's. We had something like this. Here's a side we had. Here's a side we had. But there was the angle that we were given. That angle isn't between the two sides that we were given. Side-side angle, and this is the example of the ambiguous case. Now, we're going to consider some other alternatives. Maybe we're getting different combinations of things. And if we look, if we were given all three sides of a triangle, well, we have three of the elements, but we're missing, and if you look here, we're missing a numerator in each of the pieces that would allow the law of sines to work for us. As such, if you're given all three sides of the triangle, the law of sines isn't going to help us out. And similarly, were we into a situation where we were given two sides and their included angle, side, angle, side, well, we're at least a little bit closer, sine A over A, but we only have one more value of B. We could figure out potentially what this angle is, but hey, we could still maybe have a couple scenarios because the sine of B could be in quadrant 1 or quadrant 2. And then sine C over C, we have no idea. There's myriads of options that could be working for us here. So in this case, again, the law of sines doesn't help us out. But what's nice is there's a law called the law of cosines that is going to bail us out. What it requires us, if we happen to have all three sides of a triangle, excuse me, as my view went away, or a side, angle, side, two sides and the angle in between, the law of cosines and the associated formulas that we have right here are going to do the job for us. There's three incarnations of it. It just depends on which side you happen to be solving for. You will have this formula. You will not need to prove it. You will not need to memorize it. But if we take a look, what you'll notice is, let's just use the first incarnation. A squared is a function of what? B squared, C squared, minus 2, hey, there's a B and C showing up again, times what? The cosine of angle A. What do you know? B and C are the two sides that you'll have in this scenario, and angle A you'll have. This gives us a nice, simple way to solve triangles where the law of sines won't do the job. When we get to the second page, we'll see that there's ways these formulas can also be rewritten. And we'll talk about that in a couple seconds. So let's go ahead and work through a problem. Two sides and an included angle, where the sides happen to be, lengths are 3, 7, and the angle in between these two pieces measures 130 degrees. Now in class I said I would have liked to use this triangle, but gee, we have a 130 degree angle. So this isn't going to be a realistic depiction. So I'm going to go ahead and just draw something very quickly. It'll look kind of like that. And what will I do? I'll go ahead and call this triangle A, B, C, my own way that I decide to do this. I'm going to have a value of 3, I'm going to have a value of 7, and I'm going to have a 130 degree angle in here. And what I'm going to want to solve for is the whole triangle, and there's going to be my value BC. So this isn't to scale, but again, just look at all the pieces that I have. What conditions do I have? I have two sides and an included angle. And the way I've written this, I have little c as 7. I have little b as 3. So I'll say C equals 7, B equals 3. And by the way, angle A equals 130 degrees. And so what can I do? Well, I want to solve for this piece would be the first thing to go ahead and do. Let's get my third side. A squared equals what? B squared plus C squared. 3 squared plus 7 squared minus 2 BC 3 7 times the cosine of the angle in between, cosine of 130 degrees. Now, If you run this all the way through your calculator, you're going to wind up with a squared equals, and you can do this, do it step by step. Just be careful in your calculator. You're going to come back with a squared equals 84.998. We'll just go ahead and round that to 85, which tells us that a equals the square root of 85, or 9.2. Now, what's interesting, let's think for a second. Kind of use our scorecard again. In this example, what do I happen to now have? I have 3 sides, so it's a little bit better. I started with 2 sides and included angle. I've just found my, quote, third side. So I got A, B, and C already figured out. I know angle A. All that's left for me to do is figure out what angle B and angle C are. And to do that, I can go ahead and use the law of sines now. My recommendation as we switch over is to do the following. I have 2 angles that are left. I'm going to go ahead and put my A equals 9.2 on my little scorecard. I need to get angle B and I need to get angle C. And my recommendation is always go after the biggest remaining angle. And in our case, that's going to be angle C. I can write the following. Sine of A over A, sine of 130 degrees over 9.2 equals the sine of angle C over 7. Cross multiplying, then divide by, don't even have to walk, just cross multiply each side by 7, Sine of C equals 7, sine of 130 degrees over 9.2. We'll walk into that saying sine of C is equal to 0.5828. Angle C equals the inverse sine of 0.5828, which brings me 35.6 degrees. I now have angle C equals 35.6. I'll kind of circle my little scorecard here. What's left to do? Find angle B. Well, remember, as soon as you have 2 angles, you don't need the law of sines or anything really at this stage. Just do a minus minus, as I like to say. Angle B equals 180 minus 130. That's angle A. Minus angle C, minus 35.6. And that's going to walk us into 14.4 degrees. And we're now solved for this triangle. So there's the basics. Remember, side, angle, side. 2 sides in the included angle. By the way, you might remember we also use that to do the area of a triangle with a different formula. But that same scenario, here, side, angle, side allows us to solve the rest of the triangle. All right, moving on. Let's look at a problem on our second page. And this is a nice handy formula as well that will work for you. All it is simply a rewrite of the law of cosines on the other page. It just happens to now solve for, rather than solving for one of the sides, it's going to solve for an angle. And notice in each of these formulas, what's given to you on the right-hand side? It's the values of A, B, and C. And take a look at this problem that we're given. A triangle has sides of 6, 12, and 15. And I'm going to go ahead and use the picture that I already have this time. Here's my 6, 12, and 15, and I'm going to go A, B, C. So I know that little a equals 12, little b equals 15, little c equals 6. I'm going to go after an angle using one of these 3 formulas. And what will I choose? Always as before, get the biggest angle. And that's what I'm going to do. I'm going to find the cosine of b. This is the rule of thumb. Whenever you're solving for an angle, choose the biggest one that's left. How do I know that angle b is the biggest? Because 15 is the biggest of the 3 sides. Angle b is opposite that side that measures 15. Cosine of b equals what? A squared. 12 squared. Plus what? In this case, I'm going for b, c squared plus 6 squared. Minus b squared minus 15 squared. Over 2, 12, That's how things will work. And if I work these separately, I'm going to get negative 45 over 144. B is equal to the inverse cosine of negative 45 over 144. And when I do that in my calculator, I'm going to get about 108.2 degrees. So an interesting thing, just to note, not important to a certain extent, this diagram here was just all for more my setup purposes. If I got 108.2 degree angle, I think you can all agree, you just drew 3 acute angles. This isn't a good representation. It's just a scorecard. It's just kind of a layout for me. We can draw a more precise triangle down the road. But I'm starting to solve now. I know that angle B equals 108.2. Now I could go ahead and try to solve for angle A or angle C, also using the law of cosines. There's a lot of numbers that are involved there. So you know what? I'm going to come back and use the law of sines to finish things out. You don't have to do this, but it's a nice simple way, a little bit less work maybe in the calculator plugging a bunch of numbers through. Your choice, your call. I'm going to go ahead and use the law of sines. I've already found angle C. I now am going to want to get what's left. The biggest angle in terms of how I've built this triangle, that's going to be angle A. So I know that the sine of A over 12 equals the sine of what? B, 108.2 over 15. What can I now say? That the sine of A equals 12, the sine of 108.2 divided by 15. So you see what I've done. Sine of A, multiply each side by 12. And when I do this, I'm going to come out with a value of 0.76. That tells me that angle A equals inverse sine of 0.76. And I'm going to walk into a value of, run this through my calculator real quick. Let's turn it on. There we got it already. Inverse sine of 0.76, 49.5 degrees. And again, all right, got my next piece. So I've solved one angle, there's 2 angles. I now need what? Angle C. Again, 180 minus 180 minus 108.2 minus 49.5. And I'm going to walk into 23.7 degrees. This triangle is solved. Okay, 2 more quick problems. One works on the concept of direction. A ship travels 60 miles due east and then adjusts its course 15 degrees northward. And what that means is, relative to the east, build an acute angle of 15 degrees, something like that. This little angle in here would be 15 degrees. It's made what? With the east. So this length from here to where that 15 degree change in course is made, I'm going to do that for how long? 80 miles. They want me to tell you how far the distance is between this point and this point. And so what can I do? Well, I got a side, Oh, I got an angle outside. Could I figure out what this included angle is? You're darn right I could. What do I know about this whole set of angles? It should cover what? Hey, I just drew a semicircle. Isn't that 180 degrees? And so if this side is 15, what's right here must be 165 degrees. So this little length that I want, let's go ahead. I'm just going to label for the purposes of this. That's going to be my triangle ABC this time. I'm going to want to get B. B squared equals what? Well, little a is 80. Little c is 60. Angle B equals 165. B squared equals 60 squared plus 80 squared minus 2, 80, 60, cosine 165 degrees. I'll get my hand out of the way. And when I work my way through that, I'm going to get B squared equals 19,273. 19,273. Sorry about the handwriting error there. B is equal to the square root of 19,273, which will be approximately 138.8. That's how many miles apart, how far I am from where I started. Distance from point A to point C. So you have one more problem to wrap up using the law of cosines. A parallelogram has diagonals of length 20 and 12 centimeters. The diagonals intersect to form a 60-degree angle. And so take a look at what I've drawn here. A parallelogram, intersecting diagonals, a 60-degree angle in between. Now what's also interesting about something like this is, well, this point, which should be the center of the parallelogram, might not have drawn that as perfectly as I would have liked, but give me again, little artistic license, it bisects these diagonals perfectly. So what's that telling us? That length right there is 10. This length is 10. This length is 6. That length is 6. So if I want to find the perimeter, well, if I could find out this length, if I could find out this length and then add them together, multiply by 2, need that length twice, I need this piece twice, I have exactly what I want to solve the perimeter of the parallelogram. So let's do the following. Take one more look at one more thing. 60 degrees here. This again is a line. These got to be supplemental angles. That's 120 degrees. And so if I could find that length with a triangle that has what? A side 10, side 6, and 60-degree angle in between. And if I could work with this triangle that has what? Let's make it a little bit more like this. That's a better representation. Has what? 6, 10, and 120 degrees. I'll be able to find that value. Can I do that? Absolutely. The law of cosine is going to work beautifully 2 times. This little value here, let me just call it h. I'm going to call it h for the height. I can say h squared equals what? 10 squared plus 6 squared minus 2 times 10 times 6 times the cosine of 60 degrees. And when I do that, I'm going to get h squared equals right around 76, and h equals 8.7. I've now found this part of the parallelogram, 8.7, 8.7. To work up top, well, hey, I can do something similar. I'll call this W for the width. What do I know about that W? Same thing, I got a nice lovely triangle. 6, 10, I got 2 sides, I got the angle in between. W squared equals 6 squared plus 10 squared minus 2, 6, 10, cosine 120 degrees. When I work my way through this, I'm going to come back with a value of W squared equals 196, and in turn, W equals the square root of 196, or 14. Here goes a 14. Here goes a 14. What's my perimeter? 2 times 14 plus 2 times 8.7. 28 plus 17.4. 45.4 is my perimeter. 40, and I can go with centimeters just so I have a unit. And that's the process. So there you have the law of cosines, a very powerful, very helpful tool. Remember, when you're solving for angles, particularly with the law of cosine setup, go after your biggest angle first. After you go after your biggest angle, anything else you're doing, whether you decide to stay with the law of cosines or you transition over to the law of sines to finish up your problem, make sure you always go after the biggest remaining angle. And there you have this lesson.